Continuing from where we left off in the previous video, we're now going to have a look at Kepler's second law of planetary motion. You can think of this one as being the law of areas. It's a bit of an unusual one to make sense of, so I'll go through the explanation first, or the definition, and then we'll try and make sense of it by using that other representation that we did in the last video. And the wording here is, if you think about the radius vector, so that basically is the line that joins the Sun to the planet. So when we're talking radius vector, it's not strictly speaking a radius here because it's an elliptical orbit, but we'll go with that term anyway. So that radius vector from the Sun to any planet sweeps out equal areas in equal times. Now that idea of sweeping out, it just means that if you take that line and sort of drag it over the plane in which the orbit exists, the area that's covered by that line as it's sort of dragged along represents the area that we're sweeping out here. So if we go and have a look at that other representation, so here again we have our planet on an elliptical orbit around the Sun, with the Sun located at one of the foci of the ellipse. And as we move that planet around, you'll see that it goes around that orbit. Notice that I'm not worrying so much about doing this at a correct speed, just sort of showing that the planet's on that orbit. I should mention here as well that the nature of this orbit is probably actually more relevant to something like a comet than it is to a planet. I mentioned in the last video that this is really exaggerated to help explain these concepts, but ultimately this isn't the orbit that a planet would exist on. It wouldn't be that elliptical. Now, in order to make sense of Kepler's second law, let's first of all add in that line that represents the radius vector. And as we move that planet around, you'll notice that that vector gets longer as the planet gets further away from the Sun, and then shorter again as it gets closer back to the Sun. So there's the radius vector that we're dealing with. Now, the idea of Kepler's law is that if we take a particular point in time, say the planet was located at that particular point at a particular point in time, and we made note of that and then recorded that radius vector being swept out over a particular passage of time, that area bounded by those two lines is now the area that we're interested in. So the distance from that first line through to the second line represents the distance that the planet has travelled in a given period of time. So that area corresponds to a certain amount of time passing. Now, if we continue that on a bit further, and we get around to somewhere a bit later on in the motion of this planet, let's say it's somewhere in that vicinity. So as this planet continues to move around the Sun, and if we measure the same passage of time, we would find that that would be the distance that the planet would travel, and so we'd have this area as being the area swept out in that same passage of time. So those two areas that you can see on the screen at the moment would be the same size. So for any passage of time equal to either of those two representations, the area swept out by the radius vector would always be the same. So we'll just go back across to the notes and notate this in a little bit more detail. So as I said, as the planet travels around this arc here, that distance would represent a certain passage of time, so a change in time there. That gives us an area that's swept out by the radius vector. Likewise, the passage of time moving from that first line to the second line on the left-hand side would be the same passage of time, and that would give us the same area. So you can see here then that if the passage of time is the same, the distances are clearly different. That means that the speed of the planet varies. So an important point to note there. So Kepler's second law is significant in that it explains the speed with which the planet is moving is not constant. So it's going to change, and somewhat counterintuitively, I think, the speed is actually going to be fastest at perihelion. And if you recall, perihelion is that point of closest approach around the path, and it's going to be slowest at aphelion. Now, trying to represent that in our other representation, very difficult. The mathematical relationship is far too complex for me to try and figure out in a short period of time. So we'll have a look at a few animations in class that help to explain that in a bit more detail. Like I say, it's a little bit of a tricky one to wrap your mind around, but the key thing there is that last point, that the speed of the planet's actually going to change, being faster as it's closest to the Sun and slower as it's further away from the Sun.